In developing drugs to battle cancer, we test them on increasingly complex models, starting with 2D cells, going on to animals, and then finally onto patients. Out of all the drugs first tested, about 90% of them fail somewhere along this path, wasting a lot of time and money. By testing the drugs on more complex cell models, we can discard the ineffective drugs earlier on in the process. These complex 3D models, known as spheroids, are difficult to look at using traditional microscopes. My PhD project aims to build a microscope that can take accurate images of these spheroids. But what is it that we actually look at inside the cell? We're interested in what proteins are doing, so we tag them with a fluorophore. This is a molecule that glows when hit by a particle of light, known as a photon. This process is called excitation. In a normal microscope, light is focused onto the spheroid and each photon excites a fluorophore. This means that the whole spheroid is excited and we end up measuring a blurry image. In a 2-photon microscope, light of half the energy is used, so 2 photons must hit a fluorophore at once for it to be excited. This only occurs at the focus where there's a very high photon density. So by using 2 photons instead of 1, we can see points deep inside the spheroid more clearly. By imaging various slices throughout the spheroid, we can get a picture of the full structure. A key piece of information is whether or not 2 proteins in the cell are interacting, as this can tell us what sort of effect the drug has had. Here we've tagged proteins in yellow and green, but it's not clear whether these proteins are just nearby or that they're definitely interacting. We're able to use a clever method to find this out for sure. Once our incoming light hits the fluorophore, it remains excited for a small amount of time before emitting a photon. If our proteins of interest are interacting, one fluorophore shares some energy with the other and gives off its photon more quickly. We say that its lifetime has decreased. Here you can see the yellow fluorophore has shared its energy with the green one, and therefore gives off its photon after a smaller amount of time. By measuring the amount of time it took for the photon to reach our camera, we can determine which proteins are interacting. We view how the lifetime varies in these overlapping areas to see the level of protein interaction and how well the drugs are functioning. So my microscope will be able to look at 3D structures by using 2 photons instead of 1, and whether the proteins are interacting by measuring the lifetimes. However, this technique can be quite slow, limiting the amount of drugs you can test and minimizing your statistical certainty. We'll speed up the process by focusing 6 beams of light onto the spheroid at once, allowing us to capture images 6 times faster, leading to more rapid development of cancer treatments. So it turns out that by using the lifetime, we just might increase someone else's lifetime. Thanks for listening.